There we go. Okay, so far we have only been dealing with substance like air, no? Because we can assume it's an ideal substance. But that's not the case in the vast majority of engineering applications. You're going to have substances like water or fluids that can go into different states. Okay? So let's put over here properties of substances. All right, so, and here there is a figure, a page that I told you could use. So I hope it's here. Let's see. Units, properties of pure substances. That one should be in Canvas. And basically, this is not it, but basically, I mean, let's look at it. So if you have a substance and you look at this figure, what are the different states that you can have a substance? Can be on the solid state, will be all this area over here. Can be on the vapor gas state, will be on the right of this curve, or it could be in the middle of the solid and the gas, and then it will be a liquid. Okay? What's interesting about this curve is that you can see that in order for the water, let's say water, you know, can be solid ice, liquid, or can be vapor, no? Okay? But you see that if water, you want to go from vapor to solid, you can go. You don't need to go first through the liquid state, no? Okay? And if you want a good example, maybe if you are up north, or people up north now that is very cold, what happens if you take, let's say, a boiler and inside is only steam, you go outside and just blow it outside, no? The water is going to become from steam, it's probably going to become solid ice right away. Yeah? It's not going to go directly. So this process here is called the sublimation, when you go from vapor to solid, okay? Or from solid to gas. So what it says that you can see we have one substance that can be different states, and you see that this should be defined by lines of curves, pressure, temperature, but will be pressure volume or temperature volume. So the two properties that dictate, if you want, the state of a substance looks like is the pressure and the temperature. All right? So in our case, this is not the figure we're going to be using. Okay. Will be more like this one here. So over here, what do we have? We have temperature and we have specific volume. If you remember, I told you at the beginning of the semester, is that every time you want to know the state, one of the properties is going to be intensive, the other one is going to be extensive. So it means one is going to depend on the surroundings. So I said the temperature in this room is global, no? Depends on the location, right? But it's the same all over the places. But the volume here, if we want to find the volume of this room, we could just add the volume of different blocks. So volumes is one you can add. This one is like one that is global, no? Okay? What about the pressure? Same thing with the pressure. Okay? This one is global, and this one is like you need to add it up. All right. So in those two figures, let's see if I can reduce this. Those two figures basically represent the same thing. This one is pressure volume. This one is temperature volume. Okay? So every time, if you just think about the equation PV equal RT or PV equal nRT. All right? If you want to know the state, you always need to know two things, no? Okay? You need to have two inputs. All right, so over here, this is on this figure here, I will do the figure on the notes. This is the curve. Just look at the big one here. All right, this one here. So if the substance is on the left of this curve, and let's say here this is a critical point. So if it's on the left of this point here, this is liquid. You see they call that compressed liquid region. If it's on the side of this area here of this curve, it's a gas or a superheated vapor region. All right. And if it's in the middle, where are you going to be? You're going to be in the liquid vapor region. All right. So why is that important? And the same thing happens if you look now at these figures, exactly the same. This side is compressed liquid, liquid vapor, and saturated vapor line. The only difference is that this one, when you have the temperature and the volume, you will have lines of constant pressure. Okay? And I will explain something on the notes now. So when you have temperature, you go through lines of constant pressure that go up, and when you have pressure and volume, you go through lines of constant temperature that will go down. All right? Okay, so you need to understand this figure, which is not that difficult. Okay, we're going to practice. So what happens if you are in this area here, where there is a mixture of liquid and vapor? So let's say you're boiling water. Not all the water is going to go right away from being liquid to vapor, no? The process takes a while. So as you boil it, some of the water remain liquid as some of the water becomes vapor. Okay, so how do you determine the amount of vapor? So that's where you have here this value here, x, which is called the quality factor, and basically what does it represent? If you look at it, it's just the mass of gas divided by the total mass. So this is mass of gas divided by the mass of gas plus the mass of liquid or fluid, no? So basically the x represents what, mathematically? The percentage of vapor or gas in the mixture. Okay? And this one you can find it by looking at the properties. So x is the quality factor. So once you have the quality factor x, you can define what is the volume, let's say the volume of gas that is occupied by using this equation. But you can find out, let's say you're boiling water, you can find what is the volume occupied by the vapor, what is the volume occupied by the liquid water, no? Yeah? But you can also get the values for the enthalpy, for the internal energy, and this is the entropy, which we haven't covered yet. All right? All right, so let's start doing figures. But again, you can use this on the exams. I know they will be take home, but this is something, a page that I told you can bring to the exams and bring it all the time if you have, until it becomes clear. All right. So, as we just saw over here, you can have the PV diagram and the TV diagram. You don't need to do both. If you do one, it's fine. What happens is that depending on the problem, sometimes one is preferable over the other one. Personally, I want to tell you I use a lot more the TV than the PV. Okay? I like it more, but you don't have to. So basically you do that curve over here like this. All right? And make a point over here on top and call that one CP. CP, and CP will be the critical point. All right. Okay, so why is important the critical point? It's important just because it is like a border. Okay, it's the one that defines the end of the area. So if we are on the left side of this curve, from the critical point to the left side of this curve, what is the state of the substance? I mean, to simplify, they call this compressed liquid, but let's just say this will be liquid. Okay? If you are on the right-hand side of this curve, what will be the state? Vapor or gas, okay, whatever you want to call it. And it will be exactly the same thing on this figure. It will be liquid, and this will be vapor or gas. And if you are in the middle, it will be a liquid, will be a mixture. Liquid gas, let me just call it a mixture of liquid and gas. So mixture and mixture. Okay. So let me start with the TV because the one I like the most, the one I use more often. And let me give you an example. So let's say we are cooking pasta, so we want to boil water. You put water on the pot and you put it on the stove, okay? So you start heating, so what would be the outside pressure? Would be, let's say, 1 atmosphere, no? Okay? So when you have the TV, this will go through lines of constant pressure. Okay? And you can have multiple ones, okay? This would be P1, P2. All right? But let's go back to our example of the boiling water. So let's say you put water, you put it on the stove. So this pressure here is constant. So what's going to happen? The temperature of the water is going to increase up to this point. So that means, what should be the temperature of this point? Probably if we use SI units, should be close to 100 degrees Celsius, no? Yeah? What's going to happen? What's going to happen at 100 degrees Celsius? The temperature is going to remain constant because you cannot boil water above 100. But now what's going to happen? As you keep heating, some of the water remains liquid, but some of the water becomes gas, no? Okay? So do you remember we had the X? X is the amount of gas or vapor in the mixture. So as you move along this line, what's going to happen to the X? It's going to increase. So in this case, what would be the X at this point? 0. What would be the X at this point? 1. Okay? So here, and then as soon as you reach this point, all the water will become vapor or gas, no? Now what happened? Now that you change the state, you know that you can, maybe you don't know, but you can increase actually the temperature of the gas. You can go much higher than the temperature of the liquid water, no? Okay? So, but this is still a line of constant pressure. So all this one was 1 atmosphere. Okay? So, good thing over here, you want, let's put it over here, in this point over here, you will have, let's say this one, yeah, let's say here will be X will be 0, here X will be 1. And what's important now is that you recognize that this line over here, okay, this line to the left, this line will be called here on the left hand side will be the saturation liquid. So in this case, what's going to happen? This is going to be the line where all the fluid is going to be under the liquid state, but it's saturated because as soon as we're going to move, it's going to become a mixer, no? Yeah? And this line from here to the right will be called the saturated vapor/gas. Okay? Which is what you had on this figure over here. Let's go back to this one. You see here what you have. This is a critical point. This is the saturated liquid line. Okay, from here, this is a saturated liquid line. And from here to here, this is the saturated vapor line. Okay, it's the same thing. All right, so this is the figure I like to use for the TV. You have exactly the same thing for the PV, but this time, instead of having lines of constant pressure, you're going to have lines of constant temperature. And what is different in this case is that the lines actually come from above and they go down. And again, this would be the line of critical saturated vapor or gas. And this one will be the saturated liquid. Okay, so why is this that important? These figures, you don't need both, just one. This is extremely important. From now on, you won't be able to solve the vast majority of the problems if you don't do this figure. Okay, the reason being is, what is the state over here? What do they tell you here? Compressed liquid region. What do they tell you here? Tell you here liquid vapor region. What do they tell you over here? Superheated vapor region. All right? This is from the textbook. So now if we go to the textbook, all right, what do you see over here? Properties of saturated liquid vapor, correct? What is constant? Temperature table. Properties, so this will be for which figure? This figure, okay? I mean, it doesn't matter really. Properties of saturated water, pressure table. It will be, if we look at, probably at this figure, okay? But you see, they tell you the title, saturated liquid. So vapor is this, the one over here. Then you have tables of what? Superheated water vapor. Okay? All right? So superheated water vapor will be, if your state is over here, you need to go to those tables. Okay? And if you are to this side, what tables do you need to go? To the compressed liquid. All right? So you see, you need to, you will first do this figure in the problem. You will find out what is your state 1. Let's say your state 1 can be here, and maybe your state 2 can be here, but it could also be on the mixer, or it could be over here, no? Yeah? Let's say on the problem, let's say we are cooking our pasta. They can tell you how much heat did you have to add to the pot, so that the water goes from, let's say, 20 degrees Celsius to having boiled 80% of the water, no? So one will be here, and the final state will be somewhere over here, no? Okay? So now if you need to go look for the properties, you will go here, look at the compressed liquid, you go to the tables of the compressed liquids, and when you need to find the properties here of the mixture, you will go to the, how do they call it? To the liquid vapor tables. Yeah? Okay? So once you go to the liquid vapor tables, I mean, this is with practice, you will get it. Now, it might be too much information just at once, but if you want, we can look at it very quick. All right, over here, you have the property of saturated water, okay, liquid vapor. So remember, we say these values of saturated liquid or fluid and saturated gas, okay? So, over here per x equals 0, but here what is it? This is saturated liquid, correct? This is saturated gas. So the table is going to give you the value of the V at this point over here. That would be specific heat at saturated liquid, specific heat at saturated gas. And that's what you have over here. Specific heat at fluid, they put an F. And when they put, this is something confusing, but I think if you use your logic, it's a lot easier, okay? I will explain now what does it mean. So V fluid means is liquid. VG means that everything is gas. So this point here is at this location, and the VG would be at this location. All right? And you have something similar for everything else. For the internal energy, U sub F, U sub G, H sub F, H sub G. And this is just the difference. You do this minus this is what you get, okay? This is just the difference. But, okay, so that you know what is this 10 to the 3. What is going to occupy more? Liquid water or vapor water? Vapor is going to occupy a lot more than liquid water, no? Correct? So let's see. What does that mean? Does that mean that this value has been multiplied by 1,000, or do you need it to multiply by 1,000? look at this one. They tell you that the gas is 206. So what does that mean? What would be the value here, let's say at 10? What should be, well, it doesn't change much. Let's say at 4. What should be really this value if you're going to use it? What happens if you multiply this value by 1,000? You're going to get 1,000, no? Is that more than the V gas? Does that make sense? No. So that means that this term is actually 1.0001 10 to the minus 3. So what this 10 to the 3 means is that this value has already been multiplied by 1,000. And I know it can be confusing because it can be either one, no? All right? But if you use the logic, you know that, okay, anything vapor, if it's in the vapor state, is going to occupy more volume. So that means that this is 10 to the minus 3, no? Okay, this value has already been multiplied by 1,000. Okay, I think that's a lot of information. So maybe let's start doing a problem and it will be a lot easier, okay? So maybe here on the notes, I'm going to add these points, these equations here. All right, so you can write down here, the X is the vapor, and then, all right, so we have X is the quality factor. Which is defined as the quantity of vapor or gas divided by the one of vapor plus M liquid. So basically it's the percentage of gas or vapor in the mixture. Okay, and knowing X, you can find, for example, what would be the specific value would be equal to what? What is it? V fluid plus X, V gas minus V fluid. Or you can find what would be the value of the internal energy, would be U sub F plus X, U sub G minus U sub F. Again, these are the expressions that you had over here. Okay, I'm just copying them. All right. H will be H sub F plus X, H gas minus H fluid. So this is specific volume, internal energy, enthalpy, and then later on you have the same one for the entropy. Okay, so let's do a problem over here would be the best way. Let's do here example or example. And it looks like the one I have here is 3.99, but we can change later on, okay? I don't care, from the 9th edition. So 399, steam initially at 700 psi, 550 degree Fahrenheit, undergoes a polytropic process in a piston cylinder assembly to a final pressure of 3000. Kinetic and potential energy effects are negligible. Determine the heat transfer in BTU per pound of steam for a polytropic exponent of 1.6. So they ask us to solve this problem using the ideal gas, the tables, and then the ideal gas behavior. Okay? So basically it means using equations instead of the table. So try to use more equations than tables. All right, so so let's do the problem. So there we go. All right, so this problem, if I remember properly, they say steam in a piston cylinder assembly. So This is important, okay? Piston cylinder assembly. Why is that important? Because you know we are dealing with a closed system. We haven't covered yet the other type of system, but it will be coming. So this is the, and if it's steam, what type of substance it is that we are dealing with? Water, no? Okay? So you know, next, what do you know? You know that at state 1, the pressure, I think, was 700 lbf inch squared, so 700 psi, and at the temperature, so P1, T1 was 550. May I go check now? 550 degrees Fahrenheit. Yes, and it goes to a final pressure of 3,000. All right, so state 2, P2 equal to 3,000 lbf inch square. So we need to solve for Q over M. Okay, so I'm assuming this is being heated since the pressure increases. Okay, what else do we know? To neglect the kinetic and potential energy. All right, and what else do we know is that to go from 1 to 2, this is a polytropic process. So polytropic means what? That is for the radiation, PV to the K equal to a constant, and they tell you to take K equal to, it was 1.6. All right, so before we start this problem, that's something I wanted to do before, I just forgot. But let's say we go to this table here. This is table A2, that's not what I want. Is that the temperature? Yeah, so basically, what is be the value at which the water will be saturated before it becomes vapor? It will be 100, no? What is the pressure? This is 1.014. Basically, this is very close to 1 atmosphere, no? Okay? But let's say we go to the tables where instead of having the temperatures, we have the pressure. I think is the next one. So here we have the pressure. So let's say 1 bar. Now 1 bar, let's say the atmospheric pressure. What is the temperature at which the water is going to be saturated? The water is going to start becoming, cannot be more liquid. 99.63. This is kind of what we know, no? Yeah? Okay? So you see, at 1 bar, you have all these values here. So you know this is 1, should be 100. That's why you have it over here. Okay, so in this problem, what is the substance? We're dealing with water. So we need to know what is the state. So at what state is the water when it is at 700 and 550? So for example, if you have water at 1 atmosphere and 100, and let's say 200 degrees Celsius, you know it's going to be vapor, no? Okay? But what happens if the pressure is 10 bars? Now, that temperature at which the water will start boiling is going to go up, no? Yeah? And that's what you saw. I didn't put it here, I removed it, but if you see here, what happens if you increase the pressure? You see the temperature at which the water will boil go up. That's the idea behind the pressure cookers, no? You increase the pressure, you can increase the boiling temperature of the water. All right? But again, here we are with the English units. So we need to go to the English units here. That's why I don't like this table A9. The other one has colors, so it's a lot easier to. One is like little pink, the other one is like gray. So this one is still SI units. Here also has the unit. Okay, so we are here. So let's say we go to table A3E. So this is LBF in square. So what do we know about the first one? P1 is 700. So we go to this table and we're going to look at the value. Here is the temperature, okay? 700. I pass it. So let's see, 700. What is the temperature we have here? 503. This is the temperature at which the water will start boiling, no? Yeah? So then what is the state? What's the state of the water? It's boiling, or it has already boiled? So basically, if we do, that's why I like to do the TV figure. That's why I told you need to do one of these figures. I like, in this case, you can do either one, but let's say I do the TV figure, okay? So V or U. We have this figure over here. All right, so what did we find out from table A3? Table A3 told us what? What do we have? P equal to 700. We had that T saturation was equal to 503.23. Okay? So we go back to this figure. If we have the TV figure, that means that we go with lines of constant pressure. So let's say we have this pressure here. This will be P1 equal to 700. What would be this value over here? This is the T saturation of 503.23, okay? I don't have space to put the 23, but this will be the T saturation. What is the temperature that we have in this problem? 550. So where are we? So we have 550. Let's say this will be 550. So what would be state 1? Should be on the vapor area, no? And this will be state 1. Right, so that's the first thing we know. So we know state 1, and you see there's no way to know that unless you do the figure. Okay? I mean, if you have experience, you can do it in your head, but do the figure, okay? So now, what do we know about P2? Okay, P2, let's say, let me plot it here. We know P2 here will be 3,000. Okay, so from this equation, you can say that since T1 is higher than T saturation, state 1 is vapor or gas state, okay? This is basically what we just did. So now, let's see what we can get information about state 1. So we know this. What should be this value over here? This will be here. V fluid, and this will be V gas, no? Yep. Okay. Or you can also find the value for the internal energy. We're probably going to get both. So let's see. So what do we know? State 1 is vapor gas. So which table do we need to go? To the superheated tables, no? Okay. So that should be, let's see. That should be is table A4. You see superheated water vapor tables. So what do we know? We know the pressure is 700. So we need to go to the pressure 700. 60, 140, 200, 350. We'll probably pass it here. Let me see if I can make it a bit smaller so we can have a better picture. So 700 is right over here, okay? And you see here, the first column here is V, U, H, and T. So what do we know? The temperature is 550. So it's this line over here with this line over here. All right? So it's a lot more clear on your screen. So I can go here to my document and write down table A for E at P equal 700 and T equal 550. They want to see what I'm writing. This is the thing I wrote over here. At P equals 700 and T equal 550 from table A for E. What do we get? V. So V, which represent V as state 1, will be equal to 0.728. What should be the units? Cubic feet per pound. And to save some time, I'm also going to put what should be the internal energy. U sub 1 should be 1,149 BTUs LB. All right, so again, I need this figure. Always need the figure in front of you. Okay, now I know that from here to here is going to be a polytropic process. So it's going to be either a line going in that direction or a line going up, no? So I need to find a property which is going to tell me what is this going to fall. All right, so in here, what do we know? This is a polytropic process, correct? So knowing that we have a polytropic process, I can write down what? So I can have PV to the K is equal to a constant, or I'm not going to redo the derivation. You know that you can rewrite this equation as PV, specific volume, to the K equal to a constant. Okay? I did approve that, okay? I mean, it's not a proof, it's just algebra. All right, so if we know this, what does that mean? That means that we can write down P1, V1 to the K will be equal to what? P2, V2 to the K. Do we know P1? Yes. Do we know V1? Yes. Do we know P2? Yes. So what is the only unknown? V2, no? Okay. So we can solve here for V2. So this will give us what? Let's say V2 to the K will be equal to P1 over P2 V1 to the K, which will give us that V2 is equal to P1 over P2 V1 to the K, and here whatever you want to do, you can either take the square root to the 1.6, no? Or just say this will be to the 1 over K. All right? Okay, so go ahead and do the numerical manipulation for me, please. So numerical application, this should give you what? V2 will be equal to what? P1 is 700 divided by 3000. V1, oh, we did not calculate the V1. Oh yeah. What would be V1? V1 is the one we got over here. Yes? So times 0.728 to the 1.6. And you take that to 1 to the 1.6. And that should give you V2 in cubic feet LB. Okay, so if we do the calculation, you get for this one, V2 equal to 0.293. All right, so why is that important? Because initially, how many things did we know about state 2? Only one, correct? How many things we need to know in order to determine the state? We need 2, no? Do we know 2 now? We know the pressure, we know the specific volume, no? Okay, so we can say over here, all right, so now let's look at state 2, where we know the pressure, which is 3000, and we know the specific volume to be equal to 0.293. Okay, so here there's different ways to do this, but probably I don't know if it's the easiest one or not, but let's go back to the table. Let's see. This was the other book, no? One here. So, okay, let's go back to table A3E and see what will happen at 3000. Or we can do it maybe from here. Did I have 3000 here? You can do it from either table. Let's see that we can do it from both. Let's see they have 3000 here. 2000. They have 3000. So we can even do it from this table. But I will go to the other table, to another table later on. So in this case, this is 3000, no? What is the volume at which everything will be going from mixture to gas? What is that volume? 0.0848, and that temperature will be, saturation temperature is 695.5, no? What is V2 that we just calculated? It's 0.293. So what does that mean on the figure? So V1 over here, we found V1 to be equal to what? 0.728, no? Yeah, so let's say. So we'll be way to the right. Now we know V2 is what? 0.29293. So that means that if we plot it here, it's going to go to the left, no? V2 is smaller than V1. Yes? So it's going to the left. I mean, I already put it here. And what is the state? Is so V2 is 0.293, which is much higher than the 0.048, no? Yeah? Which this 0.048 represents the value right over here. That value right over here. If you didn't want to use this table, I know it can be confusing now, but you will get this with practice. We could go to the table A3E, I'm guessing. This one, let's see if we get there. Okay, it's going to be a while, I guess. Page up, see if it goes faster. All right, so table A3 at 3000. What was the temperature that we had on the table? It was 695.5, no? Here's the same thing. What is the VG? What is the column for VG? Is the second one, no? Yeah? So we go down to this one up to 3000. What was the value you had? 0.084, no? Which is the same one, no? Okay? But that what does that mean? Is that our substance is going to be on the right-hand side of this figure. Correct? Okay? So if you want, this is 2. We'll go here through a polytropic process. PV to the K equal to C. That will be the line over here. But let me do a little bit more, not detail, but a little figure over here. So we know that V2 higher than V gas, which was equal to what? 0.084, I think. V at 3000 is 0.084. So hold on one second. Here I can put, I mean, you could have done it from either table, but let's say table A3E, which I think will be, that should be the first reflex for you, table A3E. So you know V2 is much higher than VG. So what does that mean about the state? Let me redo a small figure here. So this is V. I'm not going to redo the whole figure, just half of it. All right, so let's say we have here P1, and we know that P1 initially V1 was equal to 0.728. Now we know that V2 is 0.293, so it's smaller than V1, okay? But because it's bigger than VG, this is VG over here. All right, this point over here, we know we still be on the vapor state. So we know this is 1, this is 2, and this will be, it doesn't matter if you do the curve, this will be the figure of your process. All right, so now we know those two things over here. So we need to find V2, we know V2 at 550, okay. Can we also find okay, so we know it's right here. So we need to find now U2. Okay, so let's go back over here. So basically we know that V2 is higher than VG. So the conclusion from this line over here is that state 2 is vapor or gas. All right, so hopefully we have time to finish this problem. Okay, so now we need to find U2, okay? The energy U2 in order to finish the problem. Let's do it, and then at the end, I'll tell you why. So page 51, we need to find U2. So this is a pain, I don't know, whatever it is. Doesn't bring anything to your understanding and makes problems a lot longer. And so we need to find U2. So in order to find U2, we need to know two things. So what are the two things we know? We know that P2 is equal to 3000, and we know that V2 is equal to 0.293. Okay? So if we go to table A for E, what do we see on table A for E? V, we don't have 0.293, but we know the values at 0.2772 and 0.3086, correct? So I can write down over here, so let me see, I can write down, so let's say it would be V equal to 0.2772, 0.3086, and I know here U is 1356.2, 1408. So basically, I'll show you what I just wrote over here. So from the table, A for E, for V.2772, the internal energy is equal to 1356.6, and the at 0.3086, the internal energy is equal to 1408. Okay, so what we need to do is interpolate. So the way to interpolate, generally, I'll do it on a lecture, but here let's just do it this way. So let's call this one, can I call just this value here V1, VA, VB, U sub A, U sub B, okay? So, over here, what we're trying to find, you always put it on the y-axis. So this will be U. And what you know, you put it on the x-axis. That will be the V's. So what do we know? At V equal 0.2772, so at VA here, and let's say here, U sub A, we are at this point A, and we go to point B here, following a linear line. So this is VB, this is U sub B. What do we know in this problem? We know V2. So we know V2 here, and then we can find U2, no? I know that you know how to do this, but I'll tell you right now, every single semester, I always ask people, how do you do an interpolation? So here you have the choice. You can either go from point A to point 2 or from point B to point 2. But what is the easiest way to go from point A to point 2, no? Okay, so U2 over here, I'm just going to do it with letters, and then you can put the values. How do you go? U2 will be equal to what? At U sub A, correct? Yeah, this value plus whatever you will move here going up. What is the slope of this line? How do you find the slope? Is how much it goes up divided by how much it goes to the increase. No, it's like the tangent, if you want. So what will be the slope? Will be the slope all along this line is the same one, no? It's a linear. So you could say the slope will be U sub B minus U sub A divided by what? V sub B minus V sub A. And now, what is the increment that you need to go through? This increment over here, no? Yeah? How much will be that increment? It will be V2 minus V sub A. All right? So now, if you put the values, what would that give you? We give you 1356.2 plus 1408 minus 1356.2 divided by 0.3086 minus 0.2772 times V2 is 0.293 minus VA 0.2772. And this will give you U sub 2 in BTUs LB. So from the first principle of thermodynamics, and the value is 1382, what do we know? Heat minus work will be equal to the change in energy, but in this part we are neglecting kinetic and potential energy. All right? So that will give you here just left over with the change in internal energy. So let's say you will have here Q minus work will be equal to M U2 minus U1. So this is uppercase U, this is lowercase u for specific internal energy. So this will give you that Q, I divide everything by the mass, will be equal to U2 minus U sub 1 plus work of M. So we know U2 minus U1, correct? We just calculated, no? U2 minus U1. Do we know how to find the work done by a polytropic process? The answer should be yes. So we need to find work over M. So let me do that and still 4 minutes. So I think I can get it done. I don't know with the values. So 52, work done by polytropic process. We know work equal to the integral of PDV, okay? If you know that the specific volume is volume over specific mass, we can write that work over mass will be equal to integral of P specific volume, no? All right. Again, I'm going a bit fast. In our case, we know that PV to the K is equal to a constant. So that means that P is equal to the constant divided by V sub K. Integral of C dV over V sub K, which is the same thing as C integral of V minus K dV. Okay, I write down the equation. I will finish it next time, okay? But let me write down the equation. So 2 more lines. So this should be equal to what? Or 3 more lines. This should be equal to the integral of C of V of minus K plus 1 divided by minus K plus 1 between V1 and V2. So, okay, I'm going to do it in detail. So this should be equal to C over 1 minus K of V2 minus K plus 1 minus V1 minus K plus 1. Knowing that C can be either equal to P1 V1 to the K or P2 V2 to the K, I mean, we derived this expression multiple times. That gives you that work over mass will be equal to 1 over 1 minus K P2 V2 minus P1 V1. So finally, Q over M, which is equal to U2 minus U1 plus work per unit mass, will be equal to U2 minus U1 plus 1 over 1 minus K P2 V2 minus P1 V1. Okay, so we finish it next time with the numerical values. All right.